Hello and welcome to another video. In this video we're going to be working on distribute coins in a binary tree. And in this one you're given the root of a binary tree with n nodes where each node has a value of coins. And there's n coins in total through the whole tree. And you want to distribute the coins such that every node has one coin. And you're asked how many moves that is, and in a move you can move one coin from one node to the node next to it. Up or down. So in this case, we would move one coin here and one coin here, so that'd be two moves. In the second example, we have 3 coins here, so the first coin would have to go here and then here to get a coin here, so that's 2 moves. And then we also have to take one more coin and move it up here. And so the main thing to figure that out, this is honestly a pretty tricky tree problem, harder than most. The main thing to figure out with this problem is figure out how many moves it takes, or what you need to do, how many moves it takes to move a coin to a node, and then how many moves does it take to move a coin to the node next to it, or really how many coins you have. So let's kind of look through this big thing to understand it a little bit better. Essentially, we're going to focus on, for nodes that are next to each other, how many moves do we need, and we're going to total that up. And regardless of if it's plus or minus, it's the same amount of moves, right? Like, for example, if this whole subtree needs 3 coins, and there's 3 coins here, there's 3 moves. Where, maybe there's a bunch of coins that need to go from here to here. That's also some number of moves. So we can build it up from the bottom, because if you build from the root, it's hard to say how much you need, but if you build it up from the bottom, then you know exactly how much you either need or can provide. Because, we can build it from the bottom, and we can say, okay, we can have some coins here, and then based on how many coins we have here, the only way to get coins, if we have a bunch of coins in here, let's say all our coins are in here, the only way to get them to the rest of the tree is like this, and then all the way down. So that's kind of what we're going to do. So let's break this down. So essentially this tree, it represents, we have 3 coins here, 3 coins here, and 1 coin here. And notice, to get a coin in here, the best way to do it, or there might be another way. Yeah, there might be another way, but pretty much, if there's extra coins in here, right? If there's extra coins in here, the best way to get coins in here are through here, like this. You can do it this way, but then you'd have to send coins up here, so it ends up being the same thing, right? If I have 2 coins here, for example, I'm not gonna draw it, but let's say I have 2 coins here. I can either do this, or I can send a coin from up here somewhere, maybe like this. But then, because I still have that extra coin, I'm going to have to send this up here anyway, so it doesn't really matter. It's the same thing. So essentially, whenever we have a tree and 2 leaf nodes, we're going to check, do we need to send coins from one of them to the other or not? Right? So in this case, what we want to do with 1 coin is we want to say, okay, let's take the coin up here and then over here. And it's going to be 2 moves. So to do that is actually pretty straightforward. So we can just calculate for each node how many coins it can either bring up or need. So this node can bring up 2 coins, right? So plus 2. Because it needs 1, but it can bring up 2. This node needs 1, so it'll be minus 1. So we can represent the number of coins a node brings up or needs as a positive or negative number. And so here, the net number of coins we get in here is going to be 2 plus the value of the node itself, so 1 minus 1, right? And basically we need to fulfill basically a node is either going to do one of 3 things, right? It will either do nothing, or it will bring up coins or pull down coins. So in this case, this node will bring up 2 coins, right? Because you're basically using the fact that every node needs 1 coin. So if it has extra coins, then it has to move them up to move into other nodes. And if it doesn't have extra coins, then it needs a coin. So we know for sure that to satisfy these 2, as long as we have enough coins in here, we need 2 moves to bring these up here, and we need 1 move to bring to bring that coin down here, right? So assuming that's how many moves we need to satisfy these 2 things. We need to bring these 2 up here, and we need to move 1 down here. So essentially, you're just focusing on how many moves does it take to move coins between adjacent nodes. So for this is going to take 3 moves total. So we can just say this is going to take 3 moves total so far. And you can either do this in a global variable or in the actual like node itself, and that's what I'll do, but you can do it in a global variable, makes it a lot easier. Okay, so there's 3 moves total to satisfy this section here. So essentially after 3 moves, this will have what it needs, and this will just have 1. Now, how many coins will we have up here when we do that? So when we do that, let's actually not draw it like this. Let's leave it the way it was. So basically what's going to happen here is we're going to take 2 coins from here, bring it over here. Then we're going to take 1 coin in here. So the net number of coins is going to be, yeah, so 2 plus 1 minus 1, right? So the net number of coins is 3. Okay. So this is going to have 3 coins at the end. Oh, actually, no, it's not going to be 3. It's going to be 2, right? Yeah, because we're taking 2 up and we're bringing 1 down. So we get 1 extra and then we have 2 as well. So now from here, we basically need to figure out, like, we need to be returning something essentially, right? So from every node, we're going to be returning, how many coins are we bringing up to the node above. And so for this node, the number of coins we can return, just like for this node, is going to be, or need is going to be the number of coins you have, right? Minus 1. Because you need to have 1. So in this case, we'll just return 1 coin, right? So for this node, this will return 1 coin, because essentially we're going to take 1 of these and move it up here. And so that we don't need to handle moves or anything, but we'll return 1 coin here. Now for this node, we're going to recurse right, and then we're going to recurse left over here. So this node doesn't have any nodes that needs 1 coin, which means the number of coins it needs is -1. Now this node has 2 extra, so it will bring up 2. So now for this node, we can calculate how many moves does it take to get everything where we need it to be correct, right? So right now, after all these moves, basically our situation looks like this. So this node has 1 coin, this node has 1 coin, this node has 1 coin, and we have 1 extra coin that we bring up here. We haven't calculated the number of moves for that yet. Actually, yeah, we haven't calculated the moves, so actually it looks more like this right now. So this node has 2. Now, so this needs 1, and this needs to send away 2. So how many moves is that? Once again, if this sends away 2 coins, that's 2 moves, and this needs 1, so 1 more move. So that's 3 moves as well. So 3 moves there. Now, how many coins will this node have after that? So it will basically gain a coin, right? And it had 0, so we'll have 1. So after all of that, this coin will have 1, and this coin will now this will be like 1, and this will be 1 essentially, right? Because what happened is two coins went here, and then 1 coin went here, and we had 3 moves total. So now it looks like this. So now how many coins does this return? Well, this can't send anything up because it has the exact number it wants, so it'll basically send back 0. Now finally, this node has 1. This basically needs to send up 1 coin. So I guess that's the best way to think of it when you calculate these values for the coins, is like, do I need to send up a coin or pull down a coin? And then for every coin they need to send up or pull down, that costs 1 move, because you're just going to adjacent nodes, right? So here we're going to be sending up a coin, and here we're not going to be doing anything. So this will be 1 move. And then once we do that, then this will have 1, and then we have 1 more move. So now this won't return anything because this is like the root. Well, it will return something, but it won't return anything to like anything that called it. But essentially, this will just return 0 coins extra. So we have 7 moves total. So let's kind of go back and figure out why we had 7 moves total, exactly like what's going on from the original part. So here we go. So essentially what's going to happen is the first coin from here is going to go 1, 2, and go here, right? So that was 2 moves. And now this has 2. So that was 2. Now the next coin, let's just say, it doesn't really matter which way you do it. Let's just say it goes 1, 2. It doesn't really matter like if you send this coin all the way down here. Actually, maybe it does. No, actually, no, it does, right? Because you want to send the coins to the closest. Yeah, so you want to send this coin here, and then you want to send this coin over here. Yeah, so this coin will go 1, 2. So that'll be 2 moves. And that'll be 1 and 1. And now this will send 1 coin, like 1, 2, and then send 1 coin up. So it'll be +2, +1. And so you get 7 here. And so now hopefully you can see that, like, if you have extra coins here, the best thing to do with them, ideally, well, tied for the best at least, is just send an extra coin to its sibling, or not sibling, sibling, I guess, and then send the rest of them up. Or you could send them down, right? So you can definitely like let's do one last example. Like, let's just say, and hopefully this will make sense. Let's just say all our coins are in here. So I think this will be like another good example to go over like exactly what's going on. Because before we sent a bunch of stuff up. Now what happens if literally we just need to send down? Let's see if this still holds. So we're going to recurse all the way here, and we're going to say, okay, so this needs 1 coin. So this will be -1. And this will be -1. So essentially what we need is we need 2 coins here. And once we have 2 coins here, it takes 2 moves to get them down here. That's 2 moves. So 2. Now, how many... So these were both -1. Now, how many coins does this return or need or something? So it needed 2 for this, and it needs 1 for this. So it's going to return -3, right? And same thing for this kind of thing. So these will both be -1. So the number of moves, once you have coins here to send them to its children, is 2. So 2 + 2. And then this will return -3. Now, basically what you're saying is I need to put 3 coins here and 3 coins here. So that's 6 more moves. So in total, you need 10 moves. So let's just verify all that to make sure that's correct. So essentially 1 coin is going to go 1, 2. So that's 2 moves. 1 coin is going to go 1, 2, 4 moves, 5, 6, 7, 8. And then 1 and 10. So that's 10 total. Okay, so now that makes sense. So essentially for every node, we're just going to return the coins it needs or gets, or needs or sends, and the interaction will be from the node to its children. So for every node, you'll get the children's it needs or gets, and then the transaction will be like this way. It'll either go up or down, but the number of moves is the same for either one. So we're actually going to store the moves in the actual function, but you can use it as a global variable and make it a lot cleaner. Or not cleaner, but just like easier. But some people did say they don't like using global variables, so I'll show you how to do without it. So we can have a private function, and it'll have an int array. So we're going to store the total number of moves, which will just accumulate up the moves as we go up, and the coins we're going to be returning. So it'll be int array traverse, and it will take a tree node. So first we can say, if the node doesn't exist, we can just return 0 moves and 0 coins. So if node equals null, let's just return 0, 0. Okay, now we're going to traverse left and traverse right. So we're going to say, and our array, we'll just write this down as a thing. So our array will look like moves and then coins for each node, something like this. So we're going to get both of those. So we'll say like maybe int array left info or something equals traverse node left. Same thing for the right. Traverse node right. And let's actually break this down into further things, because we're going to be using this and it's going to be kind of confusing if we just use indices. So we'll say like int left moves equals left info 0, int left coins equals left info 1. And we'll do the same thing for the right. So actually I probably could have done that. Okay. So now we have the total, and essentially for the moves, we're just going to accumulate them up. So, like I said, if you go back to the pic, well, I guess I don't have it, but essentially the number of moves we need for the current node is actually just the absolute value of the left coins and the right coins, right? So we can say like int cur moves equals absolute value of left coins plus absolute value. Because if we have to send them up or down, it doesn't matter. As long as we have to send something, that's one move. Okay. So that's the current moves we need for like our current node. Now we also need to figure out how many coins we need to return. So maybe we can call this like int return coins or something, or cur coins. So the number of coins we need to return are actually, now we do need to add these. So we're going to say left coins plus right coins. Plus we need a coin for ourselves, so -1. And then this will be positive or negative or whatever, but essentially like here, for example, if this is -1, -1, so here we'll have -2, plus we need a coin here, so we're actually going to return -3, because we need 3 coins here to fill this out, right? 1, 1, 1. So this will be what we're going to be returning, and now we just do a return. So we can say return, and so essentially we're going to return the total number of moves, which is, like I said, we're just going to return a cumulative number. So that's going to be left moves plus right moves plus current moves, right? We're just going to accumulate that up. And then the number of coins we're returning, we already have current coins. So, and yeah, that should be, I mean, we could also do like a current moves as well. We could break this down into a variable. Oh, I guess we already did, or so we can say like total moves or something if we wanted to, so we can throw that in there, and then we can return total moves. So that would also work. But yeah, so essentially, hopefully that makes sense. Definitely tricky to think about it, and definitely tricky to draw, but hopefully it makes sense that if you have coins in subtrees, it doesn't matter if they're positive or negative. The number of moves it takes to send a coin to its parent is just 1. And the best thing to do is always to send coins from a sibling to its sibling next to it, and then send them up. Or if you need them, the only way to get them here is you have to send them from this node's parent, or from this node's parent down to the node, then down to them. So it doesn't really matter, and it works for everything. So now all we have to do is just return traverse on the root, and we want the move, so that'll be at index 0. So there we go. And we got an error. Okay, so let's double check our logic here. So if node's null, this is fine. Left info, okay, so moves is left, coins is right, that's fine, okay. So the current moves is math_abs left coins, math_abs right coins, that's fine. Total moves is left moves, right moves, current moves. Did I ever use the node value? I did not. So this is where we need to use it, right? So the current coins is the left coins plus the right coins plus the coins we actually have. So we never use that. Yeah. Curious why it doesn't say. Oh, it's because I called it a node. Okay, there we go. Should be good now, hopefully. Okay. So yeah, definitely one of the trickier. So it's still like the same kind of thing I was saying before, where you still do have like a traverse left, traverse right, do some stuff, return some stuff, but it's very tricky to figure out what to return. In this one, definitely not straightforward. So yeah, I'd expect most people to not get this one, to be honest. I think it's pretty tricky. And it's not a straightforward tree problem. And this probably wouldn't be like the best question to ask, I'd say. So it's not a big deal if you didn't get it. But once you did see it before, it's definitely not like super straightforward, even if you saw it before. So I would definitely recommend like seeing the explanation, maybe marking it down and then solving it later. Because this is like a good practice. Like it's one of those that like if you've seen it, you should do it, but if you haven't, maybe not. So as with all tree, it's all the same. So oven for like 95% of trees. And yeah, hopefully this is helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.